Okay, morning. Are you able to see the slides?
Yes, sir.
I'm changing. Just see whether you are seeing
Yes,
the
sir.
change.
Yes, sir.
Okay, thank you. Welcome to Banasthali Vidyapeeth, Department of Chemical Engineering. We are on CHE 202 Chemical Process Calculation, lecture number 10. We start with the next process parameter, temperature. Okay, coming to temperature, you have, as I just mentioned, uh, relative and absolute temperature scale. What exactly is temperature? Temperature is not kitna garami hai. That no, you touch the body and say no, oh, fever and all it. Not like that. What is exactly? See, when you heat up something, the molecules in the substance get heated and their kinetic energy starts increasing. So temperature is actually a measurement of average kinetic energy possessed by the substance. Okay. So what is the average kinetic energy possessed by the substance is what we are measuring as temperature. So in the relative temperature you have Celsius and Fahrenheit, and for this there is a zero value which is preset 0 degree C, right? And some arbitrarily defined level. And the conversion for Fahrenheit and centigrade is well known. Just to put it, degree Fahrenheit is 1.8 times degree centigrade plus 32. Sometimes this 1.8 is also written as 9 by 5. Okay, so there's a convention. You know 9 by 5 will be equal to 1.8. Okay, so don't think 9 by 5 temperature degree centigrade is a formula different from 1.8. 9 by 5 gives you 1.8. Okay. Similarly, centigrade to Fahrenheit, you have 1 by 1.8. Sorry, given in centigrade, how to convert it into Fahrenheit. Given in Fahrenheit, how to convert it into centigrade. 1 by 1.8, or remember 1.8 is 5 by 9, sorry 9 by 5. So in this case it becomes, it will go up, so 5 by 9. Okay, degrees F, 3 degrees F minus 32. So see the bracket carefully. 1 by 1.8 is outside, 3 degree F minus 32 is inside the bracket. Absolute temperature, you have the Kelvin and Rankine. This is a scale based on where the reading 0 coincides with theoretical absolute 0. Right? You know about 0 in the thermodynamics course you have studied in the first year. Absolute 0. Right? 0 entropy configuration. So Kelvin, degree Kelvin is degree centigrade plus 273.15. Many times it's just done with 273 ignoring 0.15. And then the other case, degree Rankine is degree Fahrenheit plus 459.67, which is usually taken as 460. No harm. You can take 459.67 or 460 or 273.15 or 273. Depends upon how you are rounding it off. So a quick calculation, 100 degrees to Kelvin, Fahrenheit and Rankine. So centigrade to Kelvin is at 273. Just try it. 273. Then centigrade to Fahrenheit is centigrade into 1.8 plus 32. That's 212. And then Fahrenheit to Rankine is add Fahrenheit plus 460 is Rankine. 460 plus 212 is 672 R. Or 373 Kelvin into 1.8 can also give you the R value, either way. Okay. Then you have unit temperature difference and just temperature. When temperature is used as a unit difference means when the temperature changes by a delta value, what happens? Right? Per degree of change. So then, when you are using the temperature unit difference, we will see some example. The difference in centigrade and Kelvin will be same because 273 is the common factor. Degree Fahrenheit and degree Rankine will be same because 460 is the common parameter there. And delta C will be 1.8 times delta F and delta K is 1.8 times delta R. Only when temperature is used as a unit difference. Whether temperature is used as a unit temperature, the unit temperature difference must be interpreted from the context of the equation or sentence being examined. Let's understand this with an example. See, thermal conductivity K of aluminium is at 32 degree F is given by this formula. Read it carefully. K is equal to 117 BTU per hour feet square degree F per feet. This is the unit of thermal conductivity. Now you have to find the equivalent in terms of BTU, hour, feet square. Instead of Fahrenheit, you have to do in Kelvin, and that is the main thing. Now you first understand that thermal conductivity, the temperature here, does it denote the actual temperature or a phenomena? As the temperature varies, the thermal conductivity value also varies. So the degree F here must be denoting change in temperature more than the actual value of temperature. That is how you understand the equation. So thermal conductivity is a phenomena where at different temperature you are going to have the thermal conductivity different. Okay, so any change in temperature is going to affect the thermal conductivity value. So the degree F here is actually representing change in temperature and not actual temperature. Because if the value does not change with respect to temperature, then this degree F, you know how to convert it into degree Kelvin. Convert Fahrenheit into Celsius, and Celsius into Kelvin with 273. But what is here is that it is delta F. Delta F is same as delta R. And delta F is change in Fahrenheit and change in centigrade will correspond to 1.8. Right? Change in centigrade is 1.8 times change in Fahrenheit. Change in Kelvin is 1.8 times 15. So first let's do the change and to centigrade and then Kelvin. And you know that change in centigrade is same as change in Kelvin. Delta C is same as delta K. Unit change in centigrade is same as unit change in Kelvin. So all we have to do is convert Fahrenheit into centigrade, multiplying by 1.8. So 117 BTU per hour feet square and change in temperature, delta F per feet is 1.8 times. We are using this relation. Remember, this is different from this. It's different from this. This represents the absolute Fahrenheit centigrade. This represents the unit change. The unit change in centigrade is 1.8 times unit change in Fahrenheit. So, and you know, now you by multiplying it by 1.8, you have converted the change in Fahrenheit to change in centigrade. And you know that change in centigrade is same as change in Kelvin. So no need to bring 273 because this definition holds. Right? So this gives you 117 into 1.8, that is 221 BTU per hour feet square delta H per feet. Now, this is the correct answer. Now, if somebody does this guffer of 178 BTU, this is all in the denominator. Hour, feet square, degree F per feet. Right? This is all in the denominator. Okay? Because BTU per. So you write BTU in the numerator, and in the denominator you write hour feet square, and instead of delta F, you write 1.8 plus 32, right? Because you know centigrade to Fahrenheit conversion divided by feet. That is in the formula. This is wrong. Because in this expression, the temperature is referring unit change and not absolute value. So this conversion is wrong and this is right. Let's see one more. The heat capacity of sulfuric acid as unit joule per gram mole degree C and is given by this relation. So 139.1 plus 1.56 in 10 to the power minus 1 degree centigrade. T is expressed in degree centigrade, is there. Modify the formula so that heat capacity as unit BTU, not joule. You want in BTU. You want in BTU, not in gram mole. So the units of energy is changing from joules to BTU. So we need to convert joules into BTU. We need to convert gram mole to pound mole. So pound के याद रखना 1 kg 1 pound is 454 grams. So gram mole to pound mole, degree C to degree R. Degree C to degree R. You just see this relation. Delta C is 1.8 degree F. Delta K is 1.8 degree R. So you have to convert it into R. Degree R, and T is in degree R. Now in the given relation, T is used as a specific temperature value and not as a unit temperature difference. Okay, so the Cp value going to be constant irrespective of temperature. So here T is representing the temperature and not unit temperature difference. Okay, so interpret the thing correctly. Now establish the relation between R and C. Right. So first convert. See, you know that Fahrenheit plus 460 is Rankine. First convert centigrade to Fahrenheit and then Fahrenheit into Rankine. So 1 by 1.8 minus 32. That will convert centigrade to Fahrenheit. Right. Remember the very first equation. Centigrade, Fahrenheit. 1 by 1.8 degree F minus 32 is temperature degree centigrade. Absolute value. And Fahrenheit to Rankine is 460. Okay. So now you have the relation now. How to convert centigrade to Fahrenheit. Sorry. Centigrade to Fahrenheit and then to Rankine. Now we plug this equation. We plug this equation into this. We plug this relation between centigrade and Rankine into this expression. 139.1, 1.56 in 10 to the power minus 1. So instead of T degree C, we replace it by this. Okay. So the remaining things are there. Now this will be in joules per gram mole degree centigrade. So If you expand and simplify, you get it as 215.852 plus 8.67 is 10 to the power minus 2 T degree R. Okay. Now we convert the unit, because remember we have to convert BTU to joule and also gram mole to pound mole. Because the question was convert this joule per gram mole to BTU per pound mole. Okay, so you have now done the temperature conversion. Now we do the remaining conversion. So gram mole to pound mole 454. So 1 pound is 454 grams. So this is done, and 1 BTU joule is 1055. This is a conversion for BTU joule. This is a conversion for gram mole pound mole, and you already have the remaining expression here. What is wanted in R? Degree centigrade by degree R. I hope this is clear, 460, because in this equation, this centigrade, you are converting it into Fahrenheit and then to Rankine, right? Okay, cool. So we have now substituted into this. You get Cp is equal to 23.06 plus 2.07 into 10 to the power minus 2 T. This is in degree R, BTU per pound mole, degree R. So you got the value of Cp. Now let's look at some simple multiple choice question concerning temperature. Heat capacity of a substance is given by an equation. C is equal to 800 minus 1600 T plus 25 T square, where T is the temperature in degree Fahrenheit. So here T is in Fahrenheit. What is the heat capacity of temperature is in degree Celsius? So you have 4 choices. So this expression says T is in Fahrenheit, and you have to see how the equation changes when it becomes Celsius instead of Fahrenheit. So we know the conversion from Fahrenheit to Celsius. So let's substitute it and see. Fahrenheit is 9 by 5. You know 9 by 5 is 1.8 into Tc plus 32. So this is a relation between Fahrenheit and centigrade. 1.8 Tc or 9 by 5 Tc plus 32. Now you replace in this equation, instead of T, this expression sorry, instead of T, you use this expression, and instead of T square, you use square of this term. Okay, now to simplify it, you will find that you will get 81 T square minus 24, 800, and that is in B, right answer. 81 T square minus 24,800. Remember, I have not shown the step, but you should be able to do it, because in this, instead of T, I write 9 by 5 Tc plus 32. So instead of T square, I do square of 9 by Tc plus 32, and then simplify the expression. I get 81 T square minus 24,200, which is what is correct answer B. Next question. Again, heat capacity is given by C is equal to Bt square. See, many researchers have found the relation between heat capacity and temperature. Somewhere this expression came, some research. Another research it came T is equal to BT square. T is in degree Fahrenheit and the value of B is 50. Find the value of B if T is in degree Celsius. So it means I will have a new coefficient B star, right? Instead of B, I will have a B star and I must find how it relates with B, right? So let's check that. TF is Fahrenheit 9 by 5, that is 1.8 Tc plus 32, right? So the coefficient of T square, right? So instead of T square, I'm going to write 9 by 5 Tc, 9 by 5 Tc plus 32, right? So 9 by 5 Tc, when you square it up, will give you 9 into 9 Tc square by 5 into 5. So 9 by 5 square, B star, B, originally B was 50, now it will be 50 into 9 by 5 square. 50 into 9 by 9 square is 81, 5 square is 25, that comes to 162, and C is the right answer for this question. Next, what is the temperature difference 100 degrees C in degree Rankine? Remember 100 degrees C in degree Rankine. So Fahrenheit plus 460 is Rankine, but this is 100 degrees C. So first you have to convert, integrate into Fahrenheit and then add 460. Okay, let's see how it is done. Okay, done. Temperature will be 9 by 5 into 100, right? That is centigrade plus 32. 9 by 5 is, remember, 1.8. 1.8 into 100 plus 32 plus 460, right? This comes out to be 672 R. So D is the right answer. Right answer is D. Next, what is 100 degrees C in Fahrenheit? Remember, in the previous question, we converted 100 degrees C into Rankine. Now we are converting 100 degrees C in Fahrenheit. We know the conversion. 1.8 into 100 plus 32. Right, that comes to 212 degree F. Right, so 100 degree C is same as 212 degree F. So C is the right answer. One more. What is 40 degree F in Rankine? This is a mental problem. So Fahrenheit plus 460 is Rankine. 40 plus 460 will be 500. So C should be the right answer. Oh yes, we got it. Temperature is 40 plus 460, 500 degree R. Answer is C. Now let's take the next major parameter, pressure. Like temperature told you the average kinetic energy of the substance. What is pressure saying? Pressure is normal force per unit area. Remember, this is normal force, vertical, perpendicular. Not, acting slantly. Perpendicular force, right, per unit area. So, the normal force per unit area is what is pressure. That is the definition. Now, you have something called absolute pressure and relative pressure. Absolute pressure, PA, the symbol is PA, is measured relative to a fixed reference point of zero pressure vacuum. Right? So, that is measuring absolute pressure. But what we measure normally is what is known as relative pressure or gauge pressure. You put a pressure dial, no? Like what you call, when you fill air in your car tire, they check, the pressure. So that is not giving, that is actually giving you the gauge pressure, not absolute pressure. So gauge pressure, PG, G stands for gauge, PA stands for absolute pressure. Pressure absolute, pressure gauge, or also known as relative pressure. Pressure measured relative to atmospheric pressure. So what you are measuring is actually with respect to atmospheric pressure, what is your pressure? So many pressure measurement devices measure only the gauge pressure and not absolute pressure. So normally the gadgets you see are measuring only the gauge pressure and not absolute pressure. So the relation is absolute pressure. P absolute is equal to gauge pressure plus atmospheric pressure. So gauge plus atmospheric is absolute. When using English unit, absolute pressure and gauge pressure are designated as PSIA. PSIA stands for pound per square inch absolute. Pound, force, pound per square inch absolute. PSIG, this is for gauge pressure. Pound per square inch gauge. So this A stands for absolute, this G stands for gauge. PSI is pound per square inch. Force is in pound, unit area, square inch. Now, these are some units which must be there in the back of your head. Because like you use in the dining table, spoon, fork, etc. So as chemical engineers, we keep using these data very often. So it must be always there in your hands. Okay. So what are these things? For a pressure, atmospheric pressure means 1 atmosphere. It is same as 760 millimeter mercury. It is same as 101.3 kilopascal or same as 29.92 mercury. So 760 millimeter has been converted into inch, 29.92 inch mercury or 33.91 feet water or 14.7 psi, which is pound force per square inch. Psi is pound force per inch square. So remember to keep these values in your head because they will be required every now and then. Then, how to convert the unit? 1 bar is 1.013 bar. So bar to atmosphere. This is bar, not that bar. Right? So atmospheric pressure is measured in bar. Bar is 1.013 bar is 1 atmosphere. Kilopascals. 101.3 kilopascal is equal to 1 atmosphere. 101.3 kilopascal is equal to 1 atmosphere. Torr is also used. 760 torr is equal to 1 atmosphere. And millimeter mercury, 760 millimeter mercury is 1 atmosphere. Remember, we had seen some of them here. We are just reviewing. Water, 33.94. 9194, and water converted into inch, feet into inch, 407 inches of water means it is the equivalent to 1 atmosphere pressure. PSI is pound per square inch, 14.69 pounds per square inch into is same as 1 atmosphere. Let's do some more fundas on pressure. Remember, many in chemical engineering, we handle lot of liquid and they are stored in containers, and these containers, there is a pressure measurement come when the container is empty, it has certain pressure. When the container has the chemical filled, it has another pressure. Now to understand this, we look at what is known as hydrostatic pressure. It is a pressure at the bottom of a static non-moving column of water. Assume in this tank filled with water, right? And pressure at the top is same as atmospheric pressure. Pressure at the bottom. Pressure at the bottom will be also dependent upon the amount of liquid that is standing from bottom to top. So the relation is P is equal to PO plus rho GH. P is the pressure at the bottom. This is equal to P0 is pressure at the top of the column, and rho is the density, h is the height of the fluid, and g is the acceleration due to gravity. So P is P0 plus rho GH. Let's do a small problem on calculating the hydrostatic pressure. Many years ago, you would have studied in history something called the Boston Tea Party, where the ship carrying tea from England to America was, looted by the Native Americans. That episode is known as the Boston Tea Party. You must read it in history. Boston Tea Party is something different, and in the same Boston where our MIT is also located, our Mecca for chemical engineers is MIT is also located in Boston, Massachusetts. The great Boston molasses. What is molasses? See, you know sugar cane. You see the ganne ke juice wala. What does he do? He puts it into the roller and extracts the juice, and the waste he tucks it out. That is known as bagasse, 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 which is useful as a fuel or also as raw material for making cellulose, because the waste material is nothing but cellulose, right? And then the juice is filtered and he puts in a glass and give you. But if it is in the sugar factory, after filtering, it goes for concentration where the water content is reduced and it is made into a concentrated sugar syrup, where you may use brick scale to measure, remember, and then it goes for crystallization, right? And then sugar crystals are formed. Now the waste from the sugar industry is what is known as molasses. Okay, molasses contain some amount of sugar, and when it is fermented, it forms alcohol. So the sugar plant waste is the input for alcohol industry. So in Boston, they had a big tank of molasses, and the tank broke on January 15, 1919, and in the tank it had 2.3 million gallons of crude molasses flowed from a 30-foot high storage tank that ruptured, killing 21 people and injuring 150. The tank broke and all the molasses nadi pralay ho gaya. Now the specific gravity of crude molasses is 1.4. What was the mass of molasses in the tank? Molasses in the tank in pound mass, and the pressure at the bottom in pound force per inch square. One thing we know, given the specific gravity of crude, we can find the density of crude because nothing is given, reference will be water, so we can find the density of the crude molasses, and from the density, we have some volume here, 2.3 million gallons of crude means so much volume of crude molasses. So knowing the density, we can find the mass of molasses. So our idea is clear. Remember, mass by volume is density. So mass of molasses will be density of molasses into the volume of molasses. So the definition of density is mass of molasses by velocity by volume of molasses. And how is density? Density is same as specific gravity of molasses into density of reference multiplied by Vm. So we are substituting the word Pm by SDM and the reference density. So nothing is given, it is water.
सर आपकी माइक ऑफ हो गई है.
Yes? Hello? Yeah, somebody said something? See, the mass of molasses and mass by density, mass by volume is density. So density is specific gravity of molasses into density of the reference material. And when nothing is given, it is water, right? So reference material will be water, that we know by definition. So mass of molasses will be 1.4, that is the specific gravity, into density of reference, which is water. Water density is 62.43 pound mass per feet cube into 2.3 million gallon. 2.3 into 10 to the power 6, million is 10 to the power 6, and gallon to feet cube conversion is you can check 1 feet cube is 7.48 gallon, right? So mass of molasses is going to be given by this expression, which comes to 2.69 into 10 to the power 7 pound mass. And what is the calculation for pressure at the bottom of the tank? Right, remember the tank had a height 30-foot height. Okay. Now applying the formula for hydrostatic pressure, P will be PO plus rho mgh, right? And the top pressure plus bottom pressure. Pressure at the top of the tank and pressure at the bottom of the tank. Pressure at top of tank will be same as atmospheric pressure. Remember this. At top, the pressure is going to be the atmospheric pressure. Assume standard atmospheric pressure, and standard atmospheric pressure is 14.7 pound force per inch square, right? PSI, that's what we saw, 14.7. That was the value for 1 atmosphere is 14.7 pound force per inch square. Now we substitute the values. We substitute the value rho mgh, right? And height is 30 feet. And what else? So the acceleration due to gravity, the g value is 32.174 feet per second square, right? That is the density of the molasses into g. G is the gravitation, acceleration due to gravity, and h is the height of the tank. So put it in this equation. 14.7 is PO plus rho mgh, that is rho is 1.4 into 62.43 yeah, specific gravity into density of reference 62.43 and acceleration due to gravity is 32.174 and h. So G is known, h is 30 feet. So you put it there and substitute, simplify the expression, right? You get 32.91 pound force per inch square. PSIA is pound per square inch, right? This is the value of P, pressure at the total pressure. P is the pressure on top plus pressure at bottom. Then you have manometer. Manometer for measuring the pressure. In your third year, you will be doing the laboratory course where you will be doing a manometer experiment for pressure measurement. So right now we just see the basic. You will be doing a practical later on in the lab course. Okay. Used for measuring pressure below 3 atmosphere. Manometer is usually used for measuring pressure below 3 atmosphere. It's a U-shaped tube partially filled with fluid of known density, manometric fluid. Right? Usually, mercury is used. Sometimes water may be also used. Right? So both ends of the tube are exposed to different different pressures, causing difference in the level of the manometer. So depending on the pressure from this side and this side, the manometer level will be, say, they are not equal. They will be at two different heights, and this is the height difference in the height, which is what you are measuring, right? The difference between the pressure can be calculated from the measured difference between the liquid level in this arm and the liquid level in this arm. They are calibrated. Okay. Next, manometer pressure calculation. Based on the principle, the fluid pressure must be same at any 2 points and the same height in a continuous fluid. Change in pressure, delta P will be P1 minus P2. That's the pressure this side and pressure this side. And same as rho F minus rho into GH. Rho of the fluid and rho of, remember, this space is air and this is the fluid, right? Rho of fluid minus rho of air into G into H. Okay, so here you see this picture. You are having the fluid of density rho, this normally air, and this point A and this point B, right? And this is your total height D1. This is your total height D2 plus H, right? And the manometer fluid has a density rho F. So this is the basic picture of a manometer. You have different types of manometers. Fluid flow is from left to right in all of them. This is known as open end. Both ends are open, right? And remember, you see this is at a different height, and this is the differential, right? The same level, but this level is different. And sealed end, one end is sealed, right? One end is sealed. Okay, so it may be open end or a differential or a sealed end. Manometer pressure calculation. We'll just do this small problem to wind up that lecture today. So that next class we will take up multiple choice questions on pressure. So to do this problem, you find the pressure difference between two gas tanks. Remember, this is the tank A, this is tank B, this has got gas, this has also got a gas, and between the two tanks, you have a manometer, right? And this manometer, mercury is the liquid. The barometric pressure is 700 millimeters mercury. What is the gauge and absolute pressure in tank A in millimeter mercury? We want to find the gauge and absolute pressure of tank A. Remember, here also there is a manometer. So we have to measure the gauge pressure and absolute pressure in tank A in millimeter mercury. Let's see how to go about doing it. Using the pressure difference. Remember, we just saw pressure difference, rho F minus rho into G into H. Density of mercury minus density of air into G value acceleration due to gravity, and H1. H1 is the height here. And in this manometer, this height is H2. That is the difference in mercury level between the two arms. That is, this is height. And in this case, it is between these two heights, H2. Since the tank contains gas, the density of gas can be neglected in the calculation. Right? So, PA minus PB is equal to rho Hg. This can be neglected, we have already said, into G into H1. Right? Now, this you solve for PA, you get PA is equal to PB plus rho Hg into GH1. This is the value of PA. Similarly, we'll calculate for PB. PB is PB minus 0. C, vacuum, equal to rho into G into H2. So substitute the equivalent expression for PB in the last equation for PA. Right? Now you have this expression for PB. This expression PA has also PB. Now I replace this PB by this equation. I replace this PB by this equation. So my PA becomes, instead of PB, I put this here, plus already this is there, rho HGTH1. So this rho HGTH2, PA will be rho Hg is common in both, G is also common into H2 minus H1. How do we get the density of mercury? Mercury density, you can find out from the catalog. So this is about pressure measurement. Okay, so manometer and barometer, etc. So we are going to see some questions on yes, how do we get the density of mercury? Knowing the density of mercury is not necessary if millimeter Hg is used as a unit for pressure, so that Pa is actually H2 minus H1. Pa is 860 minus 20, right? Millimeters mercury. So this is 700. So Pa is 860 minus 20. H2 minus H1 millimeters mercury. So 860 minus 20 is 840. Is this pressure in tank A absolute or not? The calculated pressure Pa is an absolute pressure since it was measured relative to a vacuum. Remember, this end is C, vacuum. So pressure measured here is actually in terms of vacuum, so it is absolute pressure. So the calculated Pa is an absolute pressure since it was measured relative to vacuum. To determine the gauge pressure, I go subtract it from the pressure here, that is 700 millimeters mercury, right? So 840 minus 700 millimeter mercury is 140 millimeter mercury. That is the Pa in the gauge. So next we will see a set of questions, multiple choice questions on pressure. We will not be able to complete it, but we will just see one or two which are very basic, which is not a unit of pressure. Bar, Newton per meter square, torque, kg per meter square. Remember, to understand this question, you should know the definition of pressure. Pressure is what? Force per unit area. So denominator must be area, meter square. And numerator must be force, right? And in this case, kg is meter square, denominator is satisfied, but numerator must be force per unit area. And kg is not a unit of force. Kg meter per second square is force, but kg is not. So C is unlikely to be. We already know bar is a measurement of pressure, torr is a measurement of pressure, Newton per meter square is a measurement of pressure. So the unit which is not pressure must be C. Let's see this. Yes. Answer is C. Pressure is force per unit area and kg per meter square cannot be a unit of pressure. That's simple as that. Next comes, what is the value of 760 torque in Pascal? Remember, I just told you. Some of these things you will have to remember. 760 torque is 1 atmosphere. Right? And 1 atmosphere is 101.3 kilopascal. Right? And you are asked to convert 760 torr in Pascal. So go step by step. 760 torr is 1 atmosphere and 1 atmosphere is 101.3 kilopascal. So 760 into 101.3, you will get it in kilopascal. Divided by 1000, you will get it in Pascal. Okay. So let's see whether our answer is right or not. Oh yes. So 101.325, that is 1.01325, right? So into 10 atmosphere, 10 to the power 5. This will be in pascals. So recollect, 760 torque is 1 atmosphere and 1 atmosphere is 101.3 kilopascal. So using these two terms, we already got 760 torr is 1 atmosphere, which is same as 101.32 kilopascal, or in terms of pascal, I took 2 decimal, 1.01325 into 10 to the power 5. One more you see. How many pascal does a bar have? 10 to the power 4, 10 to the power 5, 10 to the power 6, 10 to the power 7. So again, you know that 1.013 bar is 1 atmosphere and 101.3 kPa is 1 atmosphere, which means 101.3 kilopascal is 1.013 bar. So 1 bar is 100 kPa, right? Which is same as 10 to the power 5 pascals. One more small, which is equal to 760 millimeters of mercury. 760 millimeters of mercury corresponds to 1 atmosphere. So A must be the right answer. Yes, 760 millimeters of mercury is same as 101.325 kilopascal or 1 atmosphere. So let's do the last question. Fifth one. 1 psi equals how many kilopascals? PSI is pounds per square inch, and you have to jump to kilopascal. So go step by step, right? 14.69 psi is equal to 1 atmosphere, and 1 atmosphere is equal to 101.3 kilopascal. So we use those two relations. Let's see. Oh yes, 1 psi is 6894 pascal, which is 6.894 kilopascal. Okay, so what we'll do is several more questions we will take up in the next lecture, but I am uploading a slide with those interested can go through the remaining questions, which we will discuss in the next lecture. Whole lot of them, right? Pressure, very simple conversion. Okay, so the coming lecture we will take up the remaining problem. We have done up to problem 5 among the multiple choice, and I think we have a long list of roughly about I think 20 or 25 multiple choice questions. How many are there? 21, 22. Yes, 22. Oh, right, that's it. Okay. I've also put a YouTube video in the Google class which explains you how the pressure conversion is done. Go through it. In the next lecture, we will start with this video on, and that's about it all. Thank you. Thank you. Thank you. Please mark your attendance in the customary attendance sheet. Okay, do it and have a fine Saturday, Sunday. Right, our weekend is Tuesday. No problem. Okay, so that's about it all. Thank you and take care.